Good afternoon to everyone. Today we will start the set of lectures by Christopher Beem. He will tell us about superconformal field theories and vertex operator algebra. So you know that you can just interrupt him if you have any questions during the lecture. He will be happy to just answer them. So please, Chris, go ahead.
Okay. So thank you to my co-organizers for inviting me to give these talks, and thanks everyone for showing up. I have something of a plan for these lectures. There's going to be 3 of them, and I think the rough outline is what you see here, with the latter 2 not fleshed out yet. It's going to depend a little bit on how things go in the beginning. I'm going to be ultimately trying to describe and talk about a connection between 4-dimensional n equals 2 superconformal field theories and a class of mathematical objects called vertex operator algebras that if you come from a physics background, you already have some intuition for, but not in the language that's used in the math literature. And roughly speaking, I want to today start out reviewing important aspects of conformal field theories in 4 dimensions with n equals 2 supersymmetry that in conjunction with some technology, which is in principle sort of standard, but I'll review it at a certain level of detail, allows you to extract a sort of simplified OPE algebra out of such a conformal field theory, which is meromorphic in particular. And then in the second lecture to come in the future, I'm going to go back and develop a little bit of the formal definitions and theories of vertex operator algebras to try to clarify the extent to which these mathematical objects describe the same thing that we are getting out of this this construction in the first lecture, and then I'll try to tie it all together in the third lecture. So that's the aspiration. Okay, so I'm going to start, and I think I'm going to try to cover a fair amount of ground. So please interrupt if I'm going too fast or not explaining something in a way that would be useful. So the context is conformal field theories in 4 dimensions with n equals 2 supersymmetry, and I'm going to be taking, of course, sort of a bootstrappy perspective on these things. So front and center is going to be local operators and representation theory. So the salient thing is that instead of the usual conformal group, conformal algebra of symmetries that we have in CFTs, we have a larger superconformal algebra, which turns out to be SU 2,2/2. And if you don't speak the language of the superalgebras, this is a thing that has our usual conformal generators listed here: rotations, translation, special conformal dilatation. It has some R symmetries, which are internal flavor symmetries, which don't commute with supercharges. And it has U2, which we think of as SU2 times U1 R symmetry. And then it has a collection of Poincare supercharges that would be there in the absence of conformal symmetry. There are left-handed and right-handed spinners, which are these alpha and alpha dot indices, and they all live in doublets of the SU2R symmetry. That's what the I index is. And they have some friends, which are the so-called special superconformal generators, which are related to the Qs the same way that Ks are related to the Ps, if you want, in the usual non-supersymmetric setting. So at a purely representation theoretic level, you get a bunch of mileage out of having extra symmetry, because it means that the local operators of your theory, and so the Hilbert space on the sphere in radial quantization, is organized into representations of this bigger bigger symmetry algebra. And the relevant unitary representations of this symmetry algebra were worked out originally in a paper from 2002 by Dolan and Osborne, and I will always use the conventions and terminology from their paper because it's how I learned it. But there was also a nice paper by Clay, Thomas, and Ken a few years ago that redid this along with a lot of other superconformal representation theory that you should use as a resource if you need it. We organize, like in ordinary conformal field theories and superconformal field theories, we organize things in terms of primaries and descendants. Now the primaries not only are annihilated by the special conformal generator K, but they're also annihilated by these S's. And the superconformal primaries will live in a representation of the maximal compact subalgebra, which in this case is rotations, SU2 times SU2, dilatations, SO2 dilatation, and the R symmetry. So we label operators, we label full supermultiplets by a set of quantum numbers that tell you how the superconformal primary transforms under this subalgebra. And so they're labeled by 5 numbers, scaling dimension delta, capital R and little r, SU2R and U1R quantum numbers, and J1, J2 left and right-handed spins. And so generically, you get big supermultiplets that look like this, where you start out with a primary, which has some scaling dimension delta, and you act with lots of Qs and Q tildes, and you build a big diamond. And all of these things, sort of each dot would represent an ordinary conformal primary if you didn't have the extra supersymmetry organizing things. The real hallmark of superconformal field theories and supersymmetric field theories is the existence of exceptional operators that live in non-generic representations of the symmetry algebra. So these are called short or semi-short multiplets. And these things show up when you have operators whose quantum numbers obey some linear relations that imply that they're non-trivially annihilated by some Qs. So that's going to make this diamond smaller. So the simplest example that most people meet first, if you have an operator whose scaling dimension is equal to its U1R charge, then if you work out a couple of commutators from the n equals 2 superconformal algebra, so here's the anti-commutator of Q with its dagger, which is one of the S's. This is the adjoint in radio quantization. You get various combinations of dilatation, spin, SU2R, and U1R charges. And if you stare at this for a minute, you see that, first of all, because this is the anti-commutator of Q with its adjoint, an operator which is diagonalized by this set of quantum numbers, the combination has to be non-negative. That's the same way that we get our usual unitarity bounce in conformal field theory. But moreover, if your dimension is equal to your U1R charge, then by sort of playing around with these positivity conditions, you find out that these SU2 spin, SU2 spin, and SU2R quantum numbers have to be 0. And in addition, the operator that obeys that condition is going to have to be annihilated by both Q tilde and S tilde for all assignments of the indices. So this condition on quantum numbers implies that you have actually 4 different supercharges that have to kill this operator. And if you go back to your diamond, you find out that whereas you usually had a big diamond, you actually only have sort of a piece of the diamond there, and the others are all 0. And so these are some sort of special operators which have a supersymmetric flavor to them. And in addition, because representation theoretically, there are fewer states in these multiplets as a consequence of some relation of quantum numbers that involve the scaling dimension, importantly, oops. That means that the scaling dimension can't be renormalized. It can't be corrected if you start varying things, because then you would move outside of this setting where you had a smaller supermultiplet. So these two classes of operators that are annihilated by either the Qs or the Q tildes that I just mentioned in the Dolan and Osborne conventions are known as epsilon multiplets. They're also sometimes called n equals 2 chiral multiplets because they're annihilated by all of the supercharges of a fixed chirality. But there's a whole menagerie of other non-generic multiplets that, depending on how much you love this stuff, you have some degree of intuition for or no intuition for. So I've drawn pictures just to give people an impression, but you're not supposed to try to digest this in real time. You have multiplets that are annihilated by some of the Q's, or in this case, some of the Q tildes. So you sort of cut off the action down and to the left. And operators are annihilated by some of the Q's. The action is cut off down and to the right. You could have both. These B hat operators are killed by 2 Q's and 2 Q tildes. So you end up with this smaller square here. There are more exotic things called semi-short representations where, okay, I won't belabor the point, but the way that you actually write down the combination of Q's and Q tildes that annihilates things is a little bit more involved. This leads to things that are named C and C bar multiplets. And there's a case where you're semi-short in 2 different ways, and you get things called C hat multiplets. And then you get things that are combinations of semi-short with respect to Q's and short with respect to Q tildes and vice versa. Those gives you things called D and D bar multiplets. Okay, that was lightning fast, but it's just let it wash over you and get some feeling for the fact that there's sort of an ecosystem of different interesting supersymmetric operators out there that you might want to get a handle on for one reason or another. So you can ask whether there are sort of characteristics of your conformal field theory, your superconformal field theory, which are directly related to the presence of various types of short multiplets. And this is the case. It's the case in sort of an obvious way with respect to symmetry. So as we know from the context of ordinary conformal field theory, when you have continuous symmetries, they have some immediate sort of boring, not boring, but sort of non-sophisticated repercussions for the spectrum. So if you have some continuous global symmetry, then there's going to be a conserved current associated to it. That's the usual story. And so that's going to be some operator that are called J, A, alpha, alpha dot. I always use, or almost always use, spinorial notation for Lorentz transformation properties. So this is a vector in 4 dimensions, and it has an adjoint index with respect to some internal symmetry group. This is a conserved current. It has, I've written this wrong. It has J1 equals a half, J2 equals a half, and scaling dimension 3. And it turns out that that thing necessarily, by representation theory, lives inside of a multiplet. It's the action of 2 Q's and 2 Q, or 1 Q and 1 Q tilde on a scalar operator that I'll conventionally denote by mu, which has scaling dimension 2. It's an SU2R triplet, and the other quantum numbers are all 0. And that necessarily means, by the sorts of arguments I was making before, that this operator is the superconformal primary, so the top of the diamond, in a B hat 1 multiplet. So this is an operator which is annihilated by 2 Q's and 2 Q tildes. Similarly, just by usual arguments about locality and Poincare symmetry and supersymmetry, in a local theory, we should have a stress tensor, and in a superconformal theory, we should also have, oh, there's a question. Yes, please.
Hi, can I ask a question? So I think you already specified now, you're doing specifically D equals 4.
4 dimensions, n equals 2.
Do things also translate to other dimensions, or is this all of this only applies specifically for 4 dimensions? And is there a good reason why it's only 4 dimensions? If it's so?
Well, the stuff I've said so far morally applies completely generally, and then precisely applies only to this case. So far, we're really only talking about superconformal representation theory, and in other numbers of dimensions with different amounts of supersymmetry, you're going to have some other classification of unitary representations. And so you're going to have some other set of names for your multiplets and other diamonds. And so the details are going to be different, but you're going to tell a similar story. The bigger story that I'm trying to get to in these lectures about meromorphic OPEs and vertex operator algebras is a little bit special to four-dimensional n=2 theories. It turns out it's a little bit more general than that, but the richest version of the story is in 4D n=2. And I'll mention at the very end of this lecture, if I get to the end of it, what the other contexts are where it shows up.
Thank you.
Okay. So another example that I'll mention, because we'll see it showing up in various places, is that the stress tensor in 4D necessarily lives in the same supermultiplet as the conserved currents associated to the SU2R symmetry. And these things are different types of descendants of a scalar operator of dimension 2, whose R charges are all 0, and that thing is necessarily the top of the diamond of one of these C hat multiplets that I mentioned very briefly when I was flashing these pictures. There are other examples that I won't belabor as much. So if you have more than n=2 supersymmetry, you can think of that as a special case of an n=2 theory, in which case you're going to have extra supermultiplets corresponding to the extra supersymmetries, extra supercurrents corresponding to the extra supersymmetries. And those things will live in these multiplets that I called D and D bar, or that Dolan and Osborne called D and D bar. If you have higher spin conserved currents in your life, then those things are going to live in other C hat 0 multiplets. So C hat multiplets whose primary is an SU2R singlet, but their primaries are going to be of higher spin. And there's also some examples associated to free theories. If you have a free hypermultiplet, just the basic sort of matter operator or matter multiplet in 4D n=2, then that that's going to live in a B hat 1/2 multiplet. If you have a free vector multiplet, which is the multiplet of gauge fields, then that's going to live in a combination of Ds and D bars. Okay, so in addition to some contractual obligation to mention all of these things, I guess I want to express that sort of there's this menagerie of things that are possible representation theoretically, and then they are actually realized, and we can start to develop a bit of an opinion about what the structure of this part of the spectrum of your n=2 SCFT is based on symmetries, but that doesn't get you so far. These were some very special multiplets, and the set of representations I mentioned, there are many more. So you could look to have a little bit more intuition. We get a little bit based on moduli space physics, although this is a slightly unsettling perspective if you're a really dedicated Bootstrap person, because the connection between sort of Bootstrap data and the language of moduli spaces of vacua hasn't really been understood. Nevertheless, four-dimensional n=2 superconformal field theories, generically in all examples that I know of, that anyone knows of, I think, they come equipped with positive dimensional continuous spaces of vacua, of which the conformal field theory lives at only a particular point. And if you know something about those spaces of vacua, then you learn a little bit about the spectrum of protected multiplets. So these n=2 chiral multiplets that I mentioned earlier are what's known as Coulomb branch chiral ring operators. And if you happen to have a Lagrangian description for your theory, these things are gauge invariant combinations of the fundamental complex scalar field phi that lives in your vector multiplet. So for people who have learned some supersymmetry and know Seiberg-Witten theory, for example, these are the basic actors there. Just by unitarity, just by selection rules on the OPE, you can check that the OPE between any two of the superconformal primaries in these multiplets is necessarily non-singular. So you can define a product structure, but just by taking them and sticking them on top of each other. And that defines a fairly simple algebraic structure on these multiplets. They form some sort of commutative associative algebra. So you forget about position dependence, you're just stacking them on top of each other. And the expectation values of these operators parameterize part of the moduli space of vacua, the so-called Coulomb branch, which is the set of vacua that preserve SU2R symmetry. So remember, these primaries are charged under U and R, but not charged under SU2R. So you can give them vevs without breaking SU2R. And there's a similar story for these B hat multiplets, of which we previously met the B hat 1 in the case of conserved currents. These are what are known as the Higgs branch Cauchy ring operators. And again, these are sort of complementary to the Coulomb branch Cauchy ring operators, where instead of carrying U1R charge, they carry SU2R charge, and their dimension is determined by that R charge. And again, selection rules imply that the OPEs of these B hat multiplets are non-singular, and so you can stack them on top of each other and define a commutative associative algebra. And in all examples that we know about of 4D n equals 2 SCFTs, it's the case that these commutative associative rings or algebras, people use these terms a little bit interchangeably in the field, are the same thing as the space or as the ring of functions, ring of holomorphic functions on the relevant branch of the moduli space. And in fact, that tells you that in principle, you can characterize the moduli space of these parts of the moduli space of vacua, the Coulomb branch and the Higgs branch, based on CFT data, because if you know these rings, then you can define an algebraic variety, which is just the space defined by cutting out a subspace of affine space by the relations obeyed in this algebra. That's a thing which you can see happening in Lagrangian theories, although I'm avoiding Lagrangian descriptions in these talks. It's not clear how one should demonstrate this fact from Bootstrap principles, and that's an open question. But for my purposes, there may be times when I need to take this for granted, and I will take this for granted. So there's actually some sort of, if you have some finite dimensional algebraic variety and you have the ring of functions on it, then that ring of functions is infinite dimensional. So this actually tells you about an infinite set of these short operators, or two infinite sets, one for the epsilons and one for the b hats.
Can I ask a question?
Yeah.
So apart from the fact that this ring is infinite dimensional, does it tell you anything else particularly useful about the Carroll ring?
Sorry, tell me something interesting about, so
yeah.
So two examples. Sorry, go ahead.
Yeah, I was just wondering, okay, apart from the fact that this ring of Carroll ring is infinite dimensional, you said that this relation implies that the ring is infinite dimensional, but does it imply anything other structurally interesting about the ring? Like you said, basically any ring can be realized in this form, because you said we can always say define M as this M spec. I don't know exactly what this means, but you said that.
It's not quite any ring, because for example, if you had a no-potent element of a ring, that thing wouldn't make sense as a function on an algebraic variety. So this M spec involves getting rid of things that are no potent. There is more data here that I'm not going to go into for purposes of time. So there are things that we know based on sort of effective field theory reasoning about these moduli spaces of vacua. The Higgs branch is a hyperkähler cone. The Coulomb branch as a algebraic variety is usually pretty simple, although there's some question. So in almost all examples that people care about, it's just an affine space. So the Coulomb branch Cauchy ring usually doesn't have any relations, although you can do some exotic things to cook up some relations. so there's structure, but I must press on and not outline it. But I'm happy to come back to it in after the fact discussions.
So just to make sure, so for example, you mentioned that you cannot have a chiral, as a consequence of this, you cannot have a chiral primary which squares to 0.
That's right.
In n equal 2 supersymmetry, while in n equal 1, you could have it.
So it's for these particular types of chiral primaries. So it's not the claim that there are no short multiplets whose superconformal primaries are nilpotent. This is a statement about the set of operators that you get by taking products of these B hats, and the set of operators you get by taking products of these epsilon.
Okay.
And this is a conjecture that it follows from this general belief about the connection between these rings and the moduli space of vacua, but it hasn't been demonstrated on Bootstrap grounds.
Okay. Thanks.
Sorry, how should we think about these rings being infinite dimensional if almost every example we know has finite rank?
No. The ring as a vector space is infinite dimensional. So if you think about just the complex plane and the ring of algebraic functions on the complex plane, that's just the polynomial ring in a thing called Z. So that's infinite dimensional because you can take Z to the n for any n. But it's the ring of functions on a finite dimensional algebraic variety, if you want, because it's finitely generated. So when I say there's infinitely many, I mean that if you take the set of these, say, B hat operators as a complex vector space, then that thing's infinite dimensional. Did that answer the question?
Yeah, so functions on a finite dimensional variety is where you get something infinite dimensional.
That's right. That's right. I was really only making the point for the benefit of people who really haven't encountered these things much at all. You might wonder, once you have made these representation theoretic observations, oh, there are these various multiplets. You might ask, okay, how big a world is the supersymmetric spectrum, if you will, of a superconformal field theory? Maybe there's only the operators associated to conserved currents. Maybe there's some very small number of these special operators. If you were a pure CFT person, if you only knew the Bootstrap, it wouldn't be immediately obvious how big a world you're entering when you restrict your attention to these supersymmetric operators. And so this is an observation that it's at least an infinitely big world as a vector space. Okay, I'll proceed. Okay, so I want to move on to a slightly more sophisticated way of thinking about various classes of these supersymmetric operators, which is very much in the sort of CFT Bootstrap worldview. I'm not going to be talking about moduli spaces now. And this comes through a procedure that you might call cohomological reduction. It's a standard sort of construction in supersymmetric quantum field theory. And it involves identifying an element of the odd part of your superconformal algebra, so a supercharge that I'll generically call Q in this case, although it could also be an S, which squares to 0. And if you have a symmetry that squares to 0, you can try to treat it as a differential in the sense of chain complexes, homological algebra, cohomology, which you've hopefully at least met in sort of algebraic topology settings, if you don't already know this story. And then you can try to pass to the cohomology of that differential, which I'll say something about this in 3 different related contexts. They're closely related, so it isn't usually sort of teased apart like this, but I hope it's useful to do it in the name of being very careful. So you can sort of talk about trying to treat these supercharges cohomologically at the level of local operators, in which case you're talking about actions on some sort of a vector space. In a CFT, we know that the vector space of local operators at a point is actually a Hilbert space, so you have some more structure. You can try to extend that to the level of correlation functions, which means you're interested in being able to put operators at multiple points. And you can also try to extend this to sort of an algebraic level at the level of OPEs. And these all work. I'll say something about the different things that you should say to show that it works. But this is going to provide some sort of way of taking various structures that live in our full CFT and sort of doing a nice operation on them so that we're allowed to only focus on the supersymmetric stuff, on things having to do with these operators that are killed by some Qs. So the basic version of this story is at the level of vector spaces. So we know that in any quantum field theory, you can try to attach to a point some sort of vector space of local operators that are allowed to sit at that point. So the operator valued distributions in Slava's talk. In a CFT, the vector space is a little bit more than that. It's first of all, it's always infinite dimensional, and then it has some sort of inner product. It actually has a family of inner products because you can try to draw a sphere around your point at different radii. Different spheres will give you different inner products that are related by some similarity transform. And then the Hilbert space is some sort of completion of your infinite dimensional vector space of operators at the point with respect to that inner product. So if we have this vector space of local operators and we have an action of this Q supercharge on it, then you can define some kind of a cohomology, which in its most basic version is just saying that you can look at things that are in the kernel of your Q and you can mod out by things that are in the image of your Q, because Q squares to 0, the latter is a subset, is a vector subspace of the former. In practice, we usually have a fair amount more structure. At the very least, we have some gradings around. So if your vector space and the supercharge that you're acting on the vector space with respect some grading by an abelian group, and I've written this in equations in a pretty general way in terms of some abelian group capital gamma, but you should really be thinking of Zn, which is what it usually is. Then your vector space decomposes into some graded components, which I'll label as V with a superscript by the charges under the grading. And your supercharge acts in some definite way. So this is just saying that you have a Q which has some definite charge Q with respect to whatever charges you're using to grade your space of local operators. And then cohomology sort of factors through this decomposition into a direct sum. And so you're going to be able to write the cohomology of your vector space as a direct sum of cohomologies of definite grade. And each of those cohomologies you can think of as kernel of Q acting on a particular graded component modulo the image of Q acting on sort of a graded component that feeds into that. Under fairly reasonable assumptions that I won't go into, but they're true in all the examples I know about, you can then identify some sort of preferred representatives of the cohomology classes of your supercharge. This is like you do in Hodge theory in algebraic topology, where you associate a given cohomology group, so a given set of cohomology classes of local operators, with their so-called harmonic representatives, which are the ones that are annihilated by what you get if you take the anti-commutator of Q with its adjunct. So here you should be thinking back to what we saw in the Coulomb branch chiral ring case in these epsilon multiplets, where we had that Q dagger was proportional to delta minus R, and we ended up just focusing on the operators that were killed by delta minus R, so whose dimension was equal to their U and R charge. there's a little bit more formal structure that I want to mention, which is sort of standard boilerplate stuff, but its applications matter. So this process of passing to this big quotient by things that are in the image of Q plays well with symmetries that commute with Q and also with symmetries which are a Q commutator. So if you have a symmetry which commutes with Q, then you can show in 2 lines that symmetry acts on Q cohomology. So it acts at the level of these equivalence classes that you get by doing the vector space quotient. So if you have a representative of a cohomology class, which is some operator plus a general thing, which is Q of something, then you can see that if you act on that with your symmetry G, by linearity, that's going to be G plus G of QO. But by this relation, you can commute the Q and the G or anti-commute the Q and the G. And so you get something which is G of O plus Q of something. So that's in the cohomology class of G acting on O. This is just to say that without thinking, you can sort of pass symmetries through the cohomological reduction, through this big quotient, as long as it's a symmetry that commutes with your supercharge Q. You get a stronger result if you have a symmetry which is Q of something. So if I have some other charge Q prime in my theory, so that the commutator or anti-commutator of Q and Q prime is a symmetry G, then you can show, again, in 2 lines, that if you have an operator which is annihilated by Q and you act on it with this symmetry, then the result is in the image of Q. And you get that just by replacing G with this anti-commutator and then taking one term where Q acts directly on O and observing that that's equal to 0 for O in kernel of Q. And so you're left with one term where Q is acting on something. So your result is in the image of Q. And so at the level of this quotient, at the level of Q cohomology, that means that this symmetry acts as 0. So we say that G acts trivially on cohomology. And if you open up a homological algebra textbook, this is the statement that this map G is what's called null homotopic on your chain complex. That's some fancy term for just this fact. So coming back to the simplest example that I keep coming to, which is these epsilon multiplets, you can rediscover them as an interesting set of operators from this cohomological perspective. You introduce a supercharge, which I've labeled with a DW for Donaldson-Witten, because this supercharge is somehow related to the so-called Donaldson-Witten twist of a theory, although we won't focus on it. It's a particular combination of 2 of these Q tilde supercharges, and if you work it out, then Q and Q dagger anti-commute to this combination delta minus R. So that means that if you're looking at things which are cohomology classes with respect to this Q, then you can choose harmonic representatives, which are operators whose dimension is equal to their U and R charge. So these are exactly these epsilon multiplets. And then you can check, again, using the superconformal algebra that I've never written down, but I'm just using facts from it freely, that this supercharged Q Donaldson-Witten, it commutes with translation, so it commutes with momentum generators, but more importantly, it's actually, those momentum generators are Q commutators with something. And so that means that the action of translations gets trivialized at the level of Q cohomology in this same sense that I was describing before. And so if you're looking at some epsilon multiplets, then any derivatives of those are going to be Q exact. So we really only have the epsilons and not anything that knows about spatial dependence. The fact that you don't know anything about spatial dependence is related to the fact that this supercharge is involved in defining a topological field theory for which positions don't mean anything. But that's an aside. Okay.
I have a question.
Yes, please.
Uh,
Oh, we're getting some.
Can you mute yourself? Yeah. My question is there any natural ring structure on the cohomology class you define?
Is there a natural ring structure? Yeah, so we're gonna get to that momentarily. So I'm sort of painstakingly working my way up pedantically. So started out with vector space, and then we're gonna work our way to sort of the OPE. So if it's okay, I'll keep going, and we'll have some statements to that effect in a few slides, as it were. Okay, before getting to OPEs, I had a few lines about correlators. So maybe the next natural level of sophistication is looking at Q cohomology at the level of correlators. And the basic statement is just that correlation functions of Q closed operators, so things that are annihilated by Q, are well defined at the level of cohomology. So the operation of forming correlation functions sort of survives this quotient to cohomology. And this is, again, just a few line derivation. You just think of it as taking a given operator, which is Q closed, and changing which representative of its Q cohomology class you have in your correlation function. So I add something which is a Q variation to one of my operators in a correlator. I use linearity to pull out a term where I have just a correlation function of a Q variation. And then I use the fact that Q is a symmetry of my theory to sort of turn the Q variation of this guy, pull out the Q variation to the whole correlator, and express it in terms of Q variations of the other operators in the correlator. And under the assumption that everything is Q closed, this thing is now equal to 0 for each term in the sum. So you just get a correlation function that doesn't depend on the representatives. You can phrase this as having correlation functions of cohomology classes using this square bracket notation. And the statements about symmetries goes through this generalization perfectly well. So again, if you have symmetries that are commuting or anti-commuting with your Q, then that passes to a statement that correlation functions of Q cohomology classes sort of have a covariant action of that symmetry on them. And if you have one of these Q exact symmetries, then your correlators will in fact be invariant. So coming back to this simple example of the epsilon multiplets, you find out that your correlators are necessarily independent of the insertion point of the operators because of this Q exactness of the P of the generators of translations. And so if you want, you can say more just to be pedantic. You can say, okay, if I have these correlation functions of cohomology classes, then I can actually take my points to be arbitrarily far separated. So by cluster decomposition, they're going to factorize into a product of one-point functions. And if we're actually studying this in a conformal field theory, which is not necessarily where people usually talk about these Donaldson-Witten things, then you're actually going to get 0 for your correlation functions because one-point functions are 0 in CFT. Okay, and then this is now the statement that I think we were looking for a moment ago, which is the statement that you can also try to pass the OPE through the cohomological quotient. So if you have a CFT, then you have OPEs, which I write in the usual schematic way here. And now what you want to do and what you can do is put square brackets around everything, although you need to interpret the equations a little bit carefully if you're being super pedantic. In practice, people don't usually worry about this very much. So the way to, I think the right way to sort of treat this abstractly is, of course, to think of this equation as living in the Hilbert space on a sphere that surrounds O1 and O2, the way that we usually do in order to derive the operator product expansion. And then in that Hilbert space is that's sort of the mathematically rigorous place where you're doing this quotient and asking how things are related. And then you can show easily enough that the left-hand side of a product of operators can be replaced in Q cohomology in the Hilbert space with a product of cohomology classes here. And the right-hand side, you need to be, in the case where there's actually infinitely many terms on the right-hand side, which are non-zero in Q cohomology, you do need to be a little bit careful. This isn't something that ever really gets talked about because I don't think it's a level of idiosyncrasy which is actually necessary in order to not make mistakes. But nevertheless, if you really want to be accurate, you need to make sense of this equation that I have on the right-hand side. In the case where you have an infinite sum, you need some notion of convergence of this expression. And that means that you actually want to ideally define some sort of inner product on Q cohomology. But there isn't quite a canonical inner product on Q cohomology because Q isn't self-adjoint. You can get away with using an inner product which is induced by these harmonic representatives. So you define the inner product of two Q cohomology classes to be the inner product in the full CFT of the corresponding harmonic representatives, and then everything works. And so that's just to say that you can really make this reduction work rigorously, but like I said before, I don't know of any situation where this subtlety actually plays a role where you need to be this careful. But anyway, it works. And then you can play the same game about trivializing symmetries, now sort of using this equation as the point where you start looking at the G action. And again, you get the space-time symmetries are trivialized now at the level of the OPE. So if we come back for one final time to this Donaldson-Witten example, to the case of the epsilon multiplets, this allows you to explicitly show that in this cohomological expression, these CIJKs are going to have to be X independent. Their derivatives are going to have to be 0. And I encourage you, if you like pedantry, to prove this in an actual rigorous way in terms of, there being a Hilbert space and paying attention to this issue of convergence. But it's not, I think, it's not a crux of anything. And I would emphasize, maybe for the current sort of CFT interested audience, that this statement about being able to work at the level of the OPE is a slightly stronger statement than the statement that you get at the level of correlators, precisely because correlators might all vanish in Q cohomology, like we had on the previous slide. If you're in the conformal phase of an n=2 theory, the correlators of the epsilon multiplets are all 0. Nevertheless, you get this ring structure. Okay. Okay, so that was a fair amount of abstraction. I think it's useful abstraction, but now we can get to the point, which is a particular implementation of this general structure, which is relatively complicated, but leads to an interesting algebraic reduction. So this is the construction from a paper by myself and many collaborators, including Balt, who's here, and I don't know if any of my other collaborators are in the call, in which case I won't acknowledge them. But we wrote this paper back in 2013, where we followed exactly this sort of abstract template that I've described in a particular way, using a lot of structure in the n=2 superconformal algebra. So the relevant setup is this. You imagine taking a complex plane, so an R2 subspace thought of as a complex plane subspace inside of R4. I'll name the coordinates on that plane Z and Z bar. The transverse coordinates will be named W and W bar. I'll choose an origin so that this plane passes through the origin. And then if we look at the maximal subalgebra of the n=2 superconformal algebra that preserves that plane, or we look at a maximal subalgebra, we get something that looks like this. So inside of the n=2 superconformal algebra, we have a copy of the two-dimensional holomorphic conformal algebra, say acting on the Z coordinate. We have a copy of the two-dimensional anti-holomorphic conformal algebra accessorized with some supercharges. So this is a subset of the supercharges in my full theory. We have all of the R symmetry. We have the SU2 R symmetry, and then we have a combination of rotations in the WW bar plane and U1R. Okay, so it's not necessarily the thing that you would immediately define, but you can define it.
Sorry, Chris, so what breaks the holomorphic versus anti-holomorphic symmetry? Why is it organized like this?
What do you, sorry.
I mean, we just chose a plane, and so why Z and Z bar is not treated equivalent on the plane that you, for holomorphic, you only have SL2R, but for the others, you have this.
If you choose all of the supercharges, I mean, I'm in some sense I'm making the distinction by which subset of the supercharges I choose. If you include all of the supercharges in your superconformal algebra, you can generate rotations in the QS correlators. So you're going to generate things that don't keep this plane fixed. Is that an answer?
I understand that's not all the generators will preserve the plane. What I'm confused with is what selects the orientation on the plane. Why?
I selected it. I could have chosen one that I could have chosen a different subalgebra so that the Zs are accompanied by some supercharges that talk to them and the Z bars are not. And that would be a different maximal subalgebra. There are multiple maximal subalgebras.
I see, that's an option, I see.
But of course, I mean, in the full 4D theory, there's no distinction. So they're all related by sort of conjugation through the full group. And the important thing that I can do, given this subalgebra, is I can define a fancy supercharge, which is a linear combination of a particular one of my Poincare supercharges Q and a particular one of my special conformal supercharges S, which turns out to be this combination. I've put in here a factor of zeta, which is some general complex number, which it turns out that you can include for free, and then you can rescale it if you conjugate by a combination of dilatation and SU2R. It won't play an important role, but I'm somehow attached to it. And we can observe that this choice of supercharge is somehow intrinsically an n=2 supercharge, and it's intrinsically a conformal supercharge because it involves S's, and that's sort of the hallmark of having a conformal field theory. And it doesn't live in an n=1 subalgebra of the full n=2 algebra. So this Q here, this Q here is an SU2R highest weight, and this S is an SU2R lowest weight. So these things sort of don't live in a single component of SU2R space. And now we can turn the crank. So I have some supercharge. In principle, I can take its cohomology, and I can work out what symmetries are compatible with that cohomology, and I can work out which symmetries are trivialized by that cohomology. And this is an exercise in not even representation theory. This is an exercise in commutators in superconformal algebras. And you work out that the SL2 that acts on the Z coordinate commutes with this supercharge. And the other directions are more complicated. So first of all, if you look at translations in the transverse directions, those things don't commute with Q. It's also the case that the anti-holomorphic translations, which are generated by L bar -1, don't commute. And the rest of the SL2 bar doesn't commute. You get these things. But in the case of the SL2 bar, you can get the same right-hand side by taking Q commutators of various generators of the SU2R symmetry. You can't do the same with this guy. You can't get that by some other commutator. So translations in the transverse WW bar directions are really irreparably forbidden. You can't move around in those directions while being compatible with the truncation to Q cohomology. On the other hand, the anti-holomorphic transformations can be compensated by taking a combination of those with internal R charges. So you can define a twisted SL2, which is a diagonal subalgebra of the anti-holomorphic SL2, and a kind of SL2R, where if you've included this factor of zeta, it appears in a funny way in your definition of the SL2R. And that thing is actually Q exact. So if you repurpose, or if you reimagine your sort of anti-holomorphic coordinates in terms of this twisted SL2, then your anti-holomorphic dependence is going to be trivialized in Q cohomology. This is that statement. So in principle, already at this point, without working out more of the details, one can get to maybe one of the main punchlines, which is important since I'm heading towards running overtime, which is that just running the general machinery that we had before, this tells me that at the level of cohomology with respect to this funny supercharge, my OPE that I have in 4 dimensions, my full OPE, is going to reduce to some OPE which acts on Q cohomology classes, which is covariant with respect to the holomorphic SL2, and where the action of the anti-holomorphic SL2 is trivialized. So in particular, translations, sort of anti-holomorphic translations are trivialized. So I'm going to have an OPE which is meromorphic in the sense of depending on positions in this ZZ bar plane only through the Z coordinate. That I can already assert without working out more details. How many more minutes can I have, Miguel? Can I have 10 minutes? Can I have 5 minutes? Can I have 0 minutes?
Well,
Oh, I'm sorry, you can have 10, I'm sorry.
Thank you.
Just can I ask a quick question now that you
Yep.
have all these minutes? So
So many minutes.
zeta helps us keep track of something more than just this SL2R charge. It's
Yeah.
later.
It's so sadly, I don't think I don't think it's really going to play an important role in the lectures at any point, but I like it being there because it does keep track of the way that you're violating SU2R conservation, which is a thing that we're going to see in a moment.
Okay, thanks.
Okay, so I reached my abstract conclusion, but of course I should care what sort of world this meromorphic OPE algebra is going to operate within. And so in particular, I should ask which are the local operators that sort of survive this Q cohomology. And it's actually tied up with this twisted SL2 that I already introduced. Scrolling back up, we had the twisted L0 operator was actually the commutator of Q, this funny Q with its adjoint. So imposing that L hat 0 is equal to 0 is exactly my harmonic representative condition that I said I'd like to use in general to sort of characterize my Q cohomology classes. And L hat 0 in particular is this combination of quantum numbers. Conformal dimension minus J1 plus J2 over 2 minus R. J1 plus J2 is the generator of rotations in the ZZ bar plane. So this is like a dimension minus spin in these 2 dimensions over 2 minus R. So this is what we would normally call H bar in 2 dimensions. This is sort of the anti-holomorphic scaling dimension. And then it's modified by the SU2R charge. And a little bit of n equals 2 superconformal algebra shows that actually this quantity is the sum of two non-negative numbers. There's two sort of other Q commutators that you can take, whose right-hand sides are non-negative, and their sum gives you this quantity. So if this quantity is equal to 0, then two things are equal to 0. And so you get another condition. J1 minus J2 minus R is equal to 0. That's exactly this extra central element in my maximal subalgebra that I had before. So you get a set of operators that are characterized, their harmonic representatives are characterized by two linear relations on their quantum numbers. And this is a set of operators that are popular in the n equals 2 world. They are known as Schur operators for historically unfortunate reasons. I think it's an annoying name to have to carry around, but based on work by Leonardo and collaborators on the superconformal index in 40n equals 2 theories. And in terms of these diamonds that I was showing you earlier, these things live in the following places. So my B hat operators that I met, their superconformal primaries satisfy this condition, along with all of the Z derivatives. Of course, Z derivatives are fine because we said that the holomorphic SL2 in the ZZ bar plane commuted with my Q, so I can act with Z derivatives. A single Q descendant of the superconformal primary in D and D bar multiplets shows up. And then a twofold descendant of the superconformal primary in a C hat multiplet shows up. So for these sets of multiplets, there's a unique conformal primary along with SL2Z descendants that live in this subsector. So indeed, this is an infinite dimensional subsector, both because I have Z derivatives, so that gives me some obvious infinite dimensionality. I also argued previously that there were going to be infinitely many different B hat operators in the case where you have a Higgs branch, because those correspond to the ring of functions on the Higgs branch. So at the vector space level, going back to my sort of 3 tiers of complexity, at the vector space level, in Q cohomology, I have these Schur operators, which forms a triply graded vector space, because I had 2 linear relations, and the general operators in 40n equals 2 had 5 quantum numbers. And we can take these gradings to be SU2R quantum number, U1R quantum number, and this quantity H. You could choose other ways of parametrizing it, but this H is a natural one. H is now scaling dimension plus spin in the ZZ bar plane divided by 2. And so that's my usual sort of L0 eigenvalue for the holomorphic SL2 in the plane. So if I organize things into representations of that holomorphic SL2, then I'm going to have an additional SU2R quantum number and U1R quantum number. The things get fancy when I try to extend this to correlators and OPEs, where I need to start putting operators at points other than the origin, which is where these harmonic representatives lived. And the reason for that is that we said that I have to replace my Z bar dependence. Instead of depending through my usual anti-holomorphic derivatives, I need this twisted version of the SL2 bar acting in the ZZ bar plane. And so in practice, this means that if I want to move one of my operators to another point in the ZZ bar plane, I should write something like this, where I have the usual sort of expression that allows me to move things around, conjugating by exponentiations of momentum operators, but now I have L hats instead of L bars. And those L hats, of course, are L bars. Let me remind you, L hat minus 1 is L bar minus 1 plus zeta R minus. R minus is the lowering operator of SU2R symmetry. And so in practice, what this means, so this extra exponentiated Z bar zeta R minus acts locally nilpotently. It acts nilpotently on any given operator in a definite SU2R representation. So when I expand this exponential, I'm only going to get finitely many terms having to do with this extra term. And so when you work it out, you get operators that live at other points, which look like the usual translation of your original operator, So one of your sure operators now living somewhere else in the ZZ bar plane, plus a finite sequence of corrections which have explicit Z bar dependence coming from the Z bar in this numerator, multiplying an operator that I get by starting out with my sure operator and lowering SU2R indices a finite number of times, as many times as I have powers of Z bar. And there's some coefficients that you can work out. And the fact that when I move things around, I have to change their R symmetry polarization is doing important work for me. In particular, if I didn't do that, if I just moved my sure operators around and kept them as their sort of SU2 highest weight states where they usually live, then again, all of my correlators would be 0, just by charge selection rules. So it's only because I have this funny rule for moving operators around that I'm going to be able to have some interesting correlation functions in Q cohomology. So it's complicated, but it's important that it be complicated. Okay. So now we can go to the second layer, which was at the level of correlators, and this is just putting some equations to the words I was just using. So now, if I wanted to find a correlation function that is well defined at the level of this Q cohomology, then I'm going to have constructions that look like this. So I'm looking at some sort of K-point correlator of these sure operators, but instead of just taking their highest weights, I take their SU2R indices and I contract them a bunch of times with this little 2-vector 1, z, zeta, z bar. This is another way of encoding this translation definition that I used. And the claim is that when you do that particular thing, so of course, this is a well-defined quantity in the CFT. It's some complicated thing that depends on Z and Z bars. But when you do this construction where you piece things together in a very precise way, you're going to end up with a function which is a meromorphic function of Zs. In the case of 4-point functions, the fact that I required that these operators live on the ZZ bar plane, of course, is not an extra condition, because at 4 points, we can always move 4 points onto a plane. At 5 points, this is a more unusual looking condition because I have to do this restriction by hand. And it's an interesting historical fact that that this meromorphic property for the case where I'm looking at 4-point functions, where the operators are all of B hat type, already was derived using superconformal ward identities. So without using any sort of highfalutin language about Q cohomology, in papers from 2004 by these authors. And for those interested in the history of this particular story, it was a paper that I wrote with Leonardo and with Bolt back in 2013, where we first noticed that holomorphic function, or that meromorphic function that followed from those 2004 papers, actually obeyed its own crossing symmetry equation and therefore could be bootstrapped sort of as a meromorphic correlator. That was sort of our first indication that there was some underlying meromorphic operator algebra structure that then we could sort of reverse engineer into this whole story that I'm telling you. Okay, so my final slide, I guess. Sorry, I'm going to take 1 extra minute. I just want to show how this works at a detailed level, because I think it's instructive. So it all feels a little bit magical, or at least it used to feel a little bit magical to me. But let's look at just the most simple examples, which is where you take free fields. So there we know everything about their OPEs and their correlators, and you can just do things by hand without being fancy. And I said that if you have a free hypermultiplet, then the basic scalar operators in it live in these B hat multiplets. So in a 4D n equals 2 free matter field theory, you have dimension 1 operators Q and Q tilde that live in SU2R doublets, which are these sorts of sure operators. And so you should be able to do this procedure. And if we write it out to make everything transparent, the scalar operator Q lives in an SU2R doublet whose top component is Q and its bottom component is the conjugate of Q tilde. And similarly, Q tilde lives in a doublet whose top component is Q tilde and its bottom component is minus Q conjugate. And now we can just follow our nose. So if I build this combination I was supposed to build, which is the highest weight plus zeta z bar times 1 R symmetry lowering, and highest weight plus zeta z bar times 1 R symmetry lowering on these two free fields, I can now take the OPE. I'm going to focus on the singular terms in the OPE because they're somehow the most important down the line. And we can just evaluate the singular OPE by hand doing free field width contractions. And you're going to get a singularity from when this Q tilde star hits this Q tilde, and from when this Q hits this Q star. And of course, it's just free scalar field theory in 4 dimensions. So the singular term goes like 1 over norm squared of the distance, 1 over z minus w squared. But now we have these explicit z bars and w bars that we got, and a zeta, accompanying this twisted translated construction. And when you put them together, you get a z bar minus w bar in the numerator, which exactly cancels the anti-holomorphic dependence. And so sure enough, you end up with something that only sees a meromorphic pole instead of sort of a real analytic pole. And an analogous thing takes place. I won't narrate what's on the screen. I'll stop here. But an analogous thing takes place in the case of vector multiplets, where the basic Schur operators are certain components of P-genos. Here you need a little bit more stuff to go on. It's important that there be Fermi statistics in order to get the cancellation to work out. But again, you end up with an expression where you have a sort of free field pole where all of the anti-holomorphic dependence gets canceled by these explicit factors that live in the numerators. Okay, I'm going to stop there. There was one extra slide, but it will live perfectly well in the third lecture. So this is the abstract setup. So the punchline now with more meat on the bones is that given a 4D n equals 2 SCFT as an algebraic object with OPEs and everything, we can extract from it canonically some sort of meromorphic subsector. Well, as I'll talk about in my next lecture, sort of the proper mathematical formulation of these meromorphic OPE algebras comes through the language of vertex operator algebras. And by the time we get to the last lecture, we'll hopefully be able to discuss a little bit sort of how we should think of this set of vertex operator algebras that come out of this construction. How do they fit into the bigger world of vertex operator algebras? Are they interesting? Are they simple? Do they have nice properties? Do they allow us to predict things about the 4-dimensional theories? This will be the aim at the end of the day.
Thank you, Chris. So are there any more questions?
If you want.
I don't have a question.
Bal doesn't have questions. I have a formal question about this last page.
Yeah.
So you wrote this equation eta plus equals something with square brackets with this cohomological sign below. And then you computed the OPE. But when you computed the OPE, you just computed the OPE between whatever was inside the square brackets. So I'm not sure, like from the formal point of view, what is the point of having those square brackets there? Because I mean, how does it go into the computation of the OPE that you have those square brackets there?
That's a great point. So I sort of hid the utility of having done that in these examples because of the fact that there's no other terms that show up which are Q exact. So if I'll take this as an excuse to show the first part of the next slide, which was the case where this doesn't happen. If you look at the operator that you get in the stress tensor multiplet, you build a similar sort of thing. Now it's a little bit more complicated. And then if you work out the OPE, it's not as straightforward because it's not just free fields, but you have some control over many terms in the OPE using word identities because you're looking at OPEs of the stress tensor multiplet. And what you get when you do that OPE is a set of terms where you're getting similar cancellations of Z bar dependence. And then you also get Q exact terms, even in the singular terms. And so, okay, again, maybe I probably haven't written this in the best possible way because I defined T to have square brackets. But so maybe I should say that T
But okay, so
square brackets around all of this. And then if you, and having that in square brackets means that you can ignore this term.
Okay.
And also in the regular, even in the free field case, I didn't write out the regular terms. Of course, the OPE doesn't end with singular terms. Regular terms matter. And even in the free field case, if you go to the regular terms, you're going to have things that have non-meromorphic dependence on the positions. But it always appears next to something which is Q of something.
Okay. Okay, thanks. Now it's all clear.
More questions? Both, do you have a question?
No, I don't.
Any further questions?
Can we go back to the Donaldson-Witten twist?
Yeah.
I understood your argument for why the endpoint functions of these Coulomb branch operators vanish at the conformal point and not necessarily a generic point. But can we also think about that as a consequence of the fact that U1R symmetry is part of the superconformal algebra, but only an automorphism of the super-Poincare algebra?
I'm not sure. I don't, can you elaborate on how, so, okay, let me say something which isn't what you were saying. So you can certainly make this argument entirely based on U1R charges rather than by cluster decomposition.
Yeah.
But I don't have a sharp statement that relates that argument to the distinction between having an outer automorphism or a sub.
Well, it doesn't have to be an outer automorphism at all. Just it's part of the superconformal algebra and not part of the super-Poincare algebra. Is that enough?
I guess you could say that. So it's yeah, sure. I mean you could maybe phrase the point being that you want to explain not so much the vanishing in the conformal phase, but the non-vanishing in the non-conformal phase.
Yes.
Yeah, sure. So in the non-conformal phase, you don't necessarily have the UNR symmetry. I mean, you should be careful because of course you could try to go on the Higgs branch, for example, where UNR is not broken. So in Higgs branch physics, even though you don't have superconformal symmetry at finite scale, you have UNR charge preserved everywhere. So it's not enough. The fact that U1 isn't part of the supersymmetry algebra doesn't mean that you never have UNR as an exact symmetry in a non-conformal n=2 theory.
Okay, yeah, that's what I was looking for, whether there are subtleties to what seemed like a quick argument.
Of course, on the Higgs branch, Coulomb branch operator vevs also vanish. So
yeah,
that doesn't actually give you non-zero correlators.
Further questions, comments? Okay, if not, let's thank Chris again. So now we can take a break and we'll resume in about 40 minutes with Madalena